Hi, my name is Dean Lee, and it's my great pleasure to welcome you to the Facility for Rare Isotope Beams, or FRIB as we like to call it. Today's Saturday morning physics talk is part of an initiative called the Advanced Studies Gateway. The Advanced Studies Gateway, its purpose is to inspire people by bringing together researchers, innovators, creative thinkers, artists, performers, and building ties between Michigan State University and the greater Lansing community. Today we are honored to have Professor Witek Nazarewicz, who will be talking about is there an end to the periodic table as part of the celebration of the 150th anniversary of the periodic table. Professor Nazarewicz is a John A. Hanna Distinguished Professor at Michigan State University and the Chief Scientist at FRIB. He is a Fellow of the American Physical Society, the United Kingdom Institute of Physics, and the American Association for the Advancement of Science. He was awarded the 2012 Tom W. Bonner Prize in Nuclear Physics and the 2017 G. N. Flerov Prize from the Joint Institute for Nuclear Research. He is also the author of more than 400 scientific publications. Before beginning the program, I need to take care of a few administrative items. In the unlikely event of an alarm or some other emergency, we should exit the building through the doors through which we came. Stay together and be careful if you cross the street. If you would like more information about the Advanced Studies Gateway, you can go online to FRIB or frib.msu.edu/gateway. And the last administrative item to remind you is to silence your phones if you haven't done so already. Now, this time it's my great pleasure to introduce Professor Witek Nazarewicz.
Thank you very much. It's a great pleasure to tell you the story of the end of the periodic table, and thanks for coming during this gloomy Saturday morning. But since MSU won the game yesterday, the spirits are high. As Dean stated, so this is the third episode in our mini-series on periodic table. There were already 2 lectures before this. This one will really concentrate on the perspectives. How far can we go? How far can we push, both in terms of atoms and in terms of nuclei? So this year is the anniversary year. Okay, 150 years ago, Mendeleev proposed the first periodic table. This is a very important organizational scheme for the atoms. Okay, so my talk will be structured in the following way. I will start from introduction. I will tell you a little bit about what are superheavy nuclei and atoms. And then we'll let us go on the very wide tour, on full speculations. So where is the end of the nuclear chart and periodic table? And then I will talk about prospects at the end. Okay? So this is the original periodic table by Mendeleev. In this periodic table, he had 66 elements, which he tries to group, organize in terms of molecular weight and chemical properties. He, of course, didn't know anything about atomic structures because the structure of atoms was not there, in 1869. So it was an ingenious intuition which guided Mendeleev here. So I'm really going to talk about modern alchemy. We know that today we don't treat alchemy very seriously. Some people call it a pseudoscience, but historically alchemy played a very important role. In the search for the elixir of life, many discoveries were made, okay, and alchemy was really a forerunner to chemistry and many areas of science. So what you see here is typical alchemist looking for philosopher's stone, which was a legendary substance which was supposed to turn base metals such as mercury or lead into gold. Okay? Well, today alchemy really can be understood in terms of radioactivity. Radioactivity is the key to today's alchemy. You know, if you think what happens in the nuclear reactor, right? So uranium is transmuted into plutonium and cesium and strontium and krypton and other elements. So this is what is happening. So today's reactor is like a philosopher's stone. Okay? Actually, if you look into literature, you will see that this process of turning lead or near-lead nuclei into gold was actually performed in the laboratory in 1980. So this is the copy of the paper by experimental group from Berkeley, and this group contains Nobel Prize winner Glenn Seaborg. So Seaborgium element is named after him, and Dave Morrissey, who is a faculty member at chemistry department, and he is also a faculty at FRIB, at NSCL, okay, is a co-author. So in this experiment, they basically fragmented bismuth into many elements, and one of them was gold. So this was the direct recreation of the alchemist's dream here. And so one can ask the question, was it from the monetary point of view, was it significant? Okay, well, the 1 hour of beam time at the Berkeley lab was $5,000 an hour, and experimentalists use about a day of beam time. They produce a minute amount of gold, okay, and here is the statement from Glenn Seaborg. It would cost more than $1 quadrillion per ounce to produce gold by this experiment. So it was not very efficient, as you can see. So we are not going to make lots of money by doing this such experiments. You know, at that point, going rate for gold, the ounce of gold was $560. So traditional ways of getting gold are certainly better, but this was a demonstration principle. Okay, so this is the periodic table of elements as of 2019. Okay, so all elements are there. And so what is periodic table? So it depends. Various people understand periodic table in different ways. Okay, for chemists, this is the scheme which tries to organize elements into groups which have similar chemical properties. For physicists, periodic table corresponds to electron terms and electron configurations in atom. Okay, in either way, periodic table compresses a huge amount of information. Okay, families of elements in the periodic table have very similar properties, and they form groups. So groups are columns. So when we talk about groups, we are talking about columns, and I will pay particular attention to the last group, which is this group, which is group 18. And this is the group of noble gases, or inert gases, or rare gases. Those are all elements which are fairly inert, which are not very reactive. You know, elements like krypton, xenon, radon, and this new guy, oganesson, the recently discovered superheavy element, they are supposed to be in one group. Okay, so the periodic table, as when it was proposed, also predicted the existence of new elements, because not every element, as we know it today, was known when Mendeleev created periodic table, 66 elements on it, then, right? So early versions of periodic table, they have holes. Like, for instance, this is periodic table from 1905, and you can see that at this spot here, and this corresponds to element 43, which we call today technetium. There was nothing. Okay? So technetium is the lightest element whose all isotopes are radioactive. So technetium does not exist in nature. Okay? But it can be produced by natural processes such as beta decay. So it was actually produced or discovered in Palermo by Emilio Segre, okay, and in the beta decay of molybdenum. Okay, technetium is actually a very useful element. It's not present in nature. We can produce it, and it can be used in medical diagnostic procedures. So this is a tracer element. So even the stuff which you cannot find in nature can be produced and used. This is what FRIB will actually do. So 1937. Okay, so let me give you a very quick and hopefully painless introduction to atoms and nuclei. I need to introduce some basic vocabulary here, okay? So this is the picture of an atom, okay? So this is an atom. This little thing here is atomic nucleus. Atomic nucleus has a size of the order of several femtometers, which is 10 to the minus 15 meters. So this is the decimal point and 15 zeros, right? So very, very small object indeed. And this is electron cloud. So electrons are orbiting around the nucleus, right? And the size, typical size of an atom is angstrom. So this is 100,000 femtometers. So electrons are far away from the nucleus. Okay, the nucleus is very heavy. Nucleus is made of elementary particles which are called protons and neutrons. Okay, so it has protons, it has neutrons, and the mass of a proton is very close to the mass of the neutron. It's around 2,000 times greater than electron mass. So this guy in the middle of the atom basically takes the whole mass of the atom. Okay. Actually, 99.9% of the mass of our visible universe is stored in those little nuclei. Okay. So helium atom, for instance, contains 2 protons and 2 neutrons. So protons are blue, neutrons are red. Just kidding. Okay, but it's nice to use colors to distinguish between protons and neutrons. So atoms, all atoms can be constructed from only 3 fundamental building blocks. Electrons, which are in the cloud. Electrons are charged, they have negative charge. There are Z protons, so Z is atomic number, like for technetium is 43, right? So Z protons, which have positive charge, so there are as many protons as electrons. So usually atoms are neutral, those charges compensate. There are N neutrons, N is called neutron number, and protons and neutrons, as you can see, they are very similar, and they are called sometimes nucleons. When we talk about a nucleon, we mean either proton or neutron. And a nucleus has A, N plus Z nucleons. So this number, the A is called mass number of total number of nucleons. Okay. So this is the popular terminology when we talk about the nucleus. It is characterized by the chemical symbol, like helium, for instance. This is the number of all nucleons, 4, and this is the number of protons. And that's it. Okay, so that's the usual nuclear notation. Okay. Well, the understanding of the periodic table was provided in the beginning of the 20th century. Okay? So Niels Bohr proposed the model of the atom based on quantum physics, quantum mechanics. Okay? Well, in this model, which is still valid, and there was a Nobel Prize in 1922, electrons are moving around the nucleus in orbits. And those orbits are grouped into shells. Okay? And if one looks at energies of those orbits, so the orbits forming shells are very close to each other, they are separated by big energy gaps, okay, which correspond to those numbers of electrons, and those atoms are particularly stable because it costs energy to take an electron, say, from here, to go across the gap. And as you can see, those are all noble gases. So inert gases correspond to closed shells. Okay, so this is krypton atom. You can ask yourself, since the lowest orbits, of course, they have the lowest energy in every system, including ourselves who would like to lower the energy. So why don't we put all electrons on the lowest orbit? Then the energy would be minimum. Well, this is impossible, and this was demonstrated by Wolfgang Pauli in 1925. According to the rules of quantum mechanics, every quantum mechanical state can be occupied only by one electron, or one proton, or one neutron. Those particles are called fermions. Okay? So the organizational scheme behind periodic table is we have all those orbits, those shells, and we fill those orbits with electrons. For a given atom, we have Z electrons, and we occupy those shells by electrons, and this is what gives the atom its structure. Okay? The most important shell from the point of view of chemistry is the last one, is the outermost shell, because this is called valence shell. It's responsible for chemical properties. So this was Bohr model and Pauli exclusion principle, as we call it, defined basically Mendeleev table. From the point of view of atomic nuclei, this is the nuclear territory. We call it nuclear landscape, or the chart of the nuclides. So for every number of neutrons and number of protons, a square here indicates one isotope. The black squares correspond to stable isotopes. There are 286 stable nuclides or isotopes in nature, but there are thousands of nuclei which are unstable, which have lifetime. They can beta decay, they can alpha decay, they can fission, etc. But there are only 286 elements in nuclides which can be found on Earth. So let me give you a short historical introduction to the topic of the heaviest atoms and heaviest nuclei. We can divide the discovery of heavy nuclei into 4 periods. So the first period was really the beginning of nuclear physics, where discoveries by the Curie and then followers discovery of polonium. Polonium is just above that, right? It was the beginning of quantum mechanics here, and then the Manhattan Project in the 1940s, Second World War, marks the second period of the discovery, and plutonium was discovered during Manhattan Project. Right? Plutonium is important. It's a fuel for nuclear plants, right? And the third period, this was Cold War, competition between Russian and American labs to discover new elements, and some of those elements were discovered in a rather violent way. For instance, Einsteinium and fermium were discovered in 1952 in the debris of the thermonuclear explosion conducted at and Witek Atoll in the Pacific Ocean, right? It is interesting to know that fermium was made through the subsequent capture of 17 neutrons by uranium-238. So during this explosion, one creates very neutron-rich environment, and uranium was capturing neutrons one by one, and then there was subsequent beta decays. In this way, fermium was created. Interestingly, the same process, this neutron captures and beta decays, is responsible for the generation of heavy elements in stars, in stellar explosions such as supernova and neutron star mergers. Okay, so we can recreate astrophysical process in supernova through thermonuclear explosions. This is a very violent way of creating elements, and I'm glad that physicists did not follow this idea. We can create nowadays elements in a safe way in nuclear laboratories without destroying islands in the Pacific. And this is the fourth period in which we are now. Nowadays, physicists create elements through nuclear reactions. First, a set of new elements between atomic number 110 and 112 were discovered at German laboratory GSI in Darmstadt, in Hessen. Okay, between 1994 and 1996, they used the so-called cold fusion heavy ion reactions with bismuth and lead targets and lighter ions. So nuclear reactions using accelerators. And at some point, physicists believe that there will be no way to go beyond element 112, 113. Element 113 was discovered at Rikeni, Japan. So this is element 113, now called nihonium, with mass 278. And the probability to fuse two nuclei to produce element 113 was extremely slow. Just to give you an idea, so for physicists, the term is cross-section. Cross-section for the production of this element was extremely small. So they were basically running this experiment in Riken for 2 years. And after the end of the first year, they saw the first signature of element 113. Well, you can think about this as an exercise in human persistence or stamina. Imagine you come to the lab, you run this experiment. First day there is nothing, second day there is nothing. I can tell you 365 times, nothing. And then by the end of the year, they found something, right? Well, and every hour of beam time and facilities such as Riken is very expensive. So this was very expensive indeed, but they were gratified eventually. They got three events of element 113. But, based on this experience, there was not a lot of faith in, that we will be able to go further. But then, in Dubna, the group in Dubna in Russia, led by Yuri Oganesson, followed slightly different idea, different production mechanisms. They used the so-called hot fusion reactions with the neutron-rich calcium-48 beam, and this extended actually the domain of superheavy considerably. So during 1998, 2008, the elements with atomic numbers 114, 118 were found. Okay, so the cross-section, so probability to fuse two nuclei into one superheavy increased. Okay. Some nuclear physics, fairly elementary. Nuclear fission is an important nuclear decay. During nuclear fission, heavy nucleus splits into two usually unequal nuclei. So this is what produces energy in nuclear reactors. Okay, so it was this phenomenon was first first explained by Lisa Meitner and Otto Frisch in February 1939. And the idea behind nuclear fission is shown here. So imagine you have a nuclear droplet, and the droplet is charged. If you put enough charge on this droplet, and of course the charges of the same sign, of course, repel each other, there will be electrostatic repulsion, and the droplet will have a tendency to divide into two pieces. And you know it very well, if you produce a bubble soap and charge bubble soap, it will burst, of course, very quickly. So this is nuclear fission. And clearly, the higher charge on the droplet, the easier it is to split it, okay? So the critical parameter here is the so-called fissility parameter, which is, roughly speaking, atomic number squared divided by 50 times A, which is total number of particles. And this X becomes large as we go to the actinized and superheavy elements. So according to this simple droplet model, if X is greater than 1, the droplet would fission immediately. The fission would destroy the nucleus, okay? So for uranium-238, this X is 0.8. If you go to oganesson, X is about 1. So then you can ask yourself, how can superheavy elements exist? Well, this is because in the atomic nucleus, protons and neutrons, the building blocks of the atomic nucleus, also move in orbits, very much like electrons move in shells. So we can talk about proton shells and neutron shells, and like rare gases, which have particular stability, the nucleonic shells also have numbers which correspond to particular stability. And what is shown in this diagram here is the so-called shell energy. Shell energy is the additional quantum energy related to the existence of proton and neutron shells. And you can see that the shell energy, which is energy stabilization, is peaked at particular numbers of neutrons and protons, like numbers 28, 50, 126, 82. Very nice regular pattern. So those nuclei are called magic nuclei, and they are particularly well bound. Okay, they are more stable than their neighbors. So we know it very well. So there are lots of experimental manifestations of the magicity of atomic nuclei. But when such a diagram was produced for the first time in the 1960s, it was realized that there is this island here, which corresponds to superheavy elements, strong shell stabilization in this corner. And this is what made people believe that when one goes to this very heavy nuclei, maybe some of those will have very long lifetime. They will be so stabilized by quantum mechanics that they will live for a long time. And this is actually from the early papers on the superheavy elements. This is what people thought. Then, this is the ship. Experimentalists, physicists are going through the ocean of instability, and somewhere there on the horizon there is this mysterious island of superheavy nuclei which can live for a very long time. Okay? Well, let us go back to reality, because I think that very few people today believe that there are very long-lived superheavy elements. But let me show you how was oganesson produced. A short story of oganesson. So it was discovered in the Dubna lab in 2002-2006. Okay, oganesson has 118 protons and electrons. Okay, so in those experiments they used calcium-48 beam, very neutron-rich, stable nucleus. They bombarded Californium target. The target was actually produced at Oak Ridge National Laboratory in Tennessee. And this is interesting thing to mention. because this was a collaboration between Oak Ridge, Livermore Lab, and Dubner. And you remember the third period of superheavy, in the history of superheavy nuclei, was this Cold War between Russia and the US. And here in the fourth period, in US and Russia collaborate on the production of superheavy elements. The times are changing, right? So calcium is bombarding californium. Those two merge together, produce one compound nucleus, which is excited, rather hot, dizzy, right? And it has to lower its energy by removing 3 neutrons. Those are neutrons, okay? And this is how oganesson 294 is produced. It is unstable. It decays by emitting alpha particle, 2 protons, 2 neutrons. This goes to livermorium. This goes to fluorovium, to copernicium. All those are alpha decay, and copernicium fissions into 2 fragments. Okay? So a number of such events were measured, and this discovery was blessed by International Union for Pure and Applied Chemistry and Physics in 2015, and it was the element was named oganesson in 2016. To honor the leader of this experimental collaboration, and this is Yuri Oganesyan on the postdoc of Armenia. He's working in Russia, but he has Armenian roots, so the Republic of Armenia honored him by issuing a postdoc. So for nuclear physicists, it's wonderful to see a decay chain on a postdoc. Okay, few comments about oganesson. Okay, so those are calculations of densities of neutrons and protons, total densities in various nuclei. This is alpha particle helium-4. This is oxygen 16. Lead-208, as you can see by looking at this number, is 8. This number is increasing. This is oganesson 294. So you can see that oganesson is really big. Those super heavy nuclei are really huge, okay, in terms of space. Okay. So oganesson is big. Oganesson and its neighbors will also have very interesting property since those Coulomb interactions or electrostatic repulsion between protons is huge in such systems. There is a fight or competition between nuclear force, which wants to cluster everything together, bind the system, and this electrostatic repulsion, which is destructive. As a result, the densities of those super heavy elements are expected to have some depression in the interior. So these are the calculated proton densities of the oganesson. You can see there is a dip. If I would calculate those densities for still heavier element, not with Z118, but say with Z150, this dip here would become, would go down to 0. There would be no matter in the interior of this very heavy system. So those would be nuclei which would look like donuts, with a void in its interior. So very interesting stuff for nuclear physicists to think of. Okay, so this is where we are today in terms of the nuclear chart. This is the very corner of the nuclear landscape, nuclear chart. So those are this heaviest actually nuclei which were produced by scientists: oganesson, tennessine, livermorium, moscovium, fluorovium, nihonium, copernicium. Okay? According to theoretical models, the area in which lifetimes of those isotopes will be significant is somewhere here. Okay? So many neutrons to the right. So this is the neutron number. In order to get here, we need experimentally to pump many neutrons into the nucleus. And this is not going to be easy because of the lack of beams and targets. Okay? Experimental data, so those are the experimental lifetimes, half-lives of those elements, suggest that indeed, as we increase neutron number towards 184, the lifetimes go up. So the current data suggests that indeed, as we produce more neutron-rich systems, the lifetimes increase. So it is important to go to the right. But this is not going to be easy. New reaction mechanisms must be invoked, and I illustrated this by means of this Pony Express. It will take lots of work and time to go there. FRIB will have its place here. FRIB, by producing radioactive neutron-rich beams, will explain the reaction mechanisms which can be then used to produce new superheavy elements. So there is a niche, a very interesting niche of research for facility for isotope beams here in East Lansing. Let me make a few comments about chemistry, because chemistry is quite fascinating when one goes to superheavy elements. So this is actually a real monument to the periodic table in Bratislava in Slovakia, a very nice one, okay, which shows periodic table in this unusual star-like configuration. So this is the corner of the periodic table today, right? So those are those new superheavy elements which I discussed. So oganesson, as you can see, is at the very end here, at this corner. Oganesson is the last nucleus, or last element, which ends group 18, rare gases, and period 7. Periods are rows, groups are columns. Okay? So with oganesson, period 7 has been completed. Okay? It's interesting to know that all those elements here, they are main group elements for chemists. They correspond to S and P electrons in the outer valence shell. Okay, so this is the largest periodic table created by humans. This is the facade of the chemistry faculty building at the University of Murcia in Spain. And you can see they got it all right. Oganesson, tennessine, livermorium is here. Okay, well, the interesting question is, what are they going to do when physicists produce elements 119 and 120? There is not a lot of room here, right? So some serious engineering will be in order. Okay. So there is a great, actually, elemental haiku published in the Science magazine. Every element, if you click on this link, you will see haiku for every element. So I just quote two haikus, one for oganesson and one for yet unknown element 119. So oganesson, the end of the line, your millisecond half-life brings down the curtain, because it's the last one, right? And what about element 119? Okay, will the curtain rise? Will you open the 8th act? Claim the center stage. 8th act, of course, is period. So very, very interesting suggestion. So why is chemistry important? Well, the secret lies in this parameter alpha, which is one of the most important fundamental physics constants, which is called fine structure constant. It's fascinating, actually, physical constant, because 1 over alpha is very close to 137. This is a combination of other constants, which are also fundamental. But 1 over alpha is 137. According to relativistic model of the atom, okay, the important quantity here is atomic number times alpha, Z times alpha. Okay, if Z times alpha is equal or greater than 1, atomic model, relativistic equation for atom becomes totally unstable. Hell breaks loose. Antimatter is produced spontaneously. Okay? So according to this relativistic quantum mechanics, at element number 137, there should be no more nuclei, right, and will produce electron-positron pairs. So people speculated at that point, when this was realized, that perhaps the last element is 137. Nothing, there are no atoms beyond it, okay? And so would element 137, Feynmanian, really spell the end of the periodic table? Well, not so quick. This equation it corresponds to the situation, this limit 137, in which the nucleus in the middle of the atom is point-like. But in fact, the charge inside the nucleus is distributed in the final volume. I showed you the plot showing the oganesson is quite a big fellow, even on a femtometer scale. So if one considers the finite size of the nucleus, this limit 137 is moved to 136. Not just you flip those two numbers here. This is so we are still very far from there. Nevertheless, Z times alpha for oganesson is 0.86, which means that relativistic effects will be tremendous in nuclei like oganesson. The electrons, which are closest to the nucleus, move with velocities which are very close to the velocity of light. They're extremely fast. And this, of course, wreaks havoc in nuclear and atomic environment. So this shows example, actually, of the so-called electron localization function for noble gases. Those are relativistic calculations. So what is important to realize here is that those rings correspond to those shells, electron shells. So you see that in non-relativistic quantum mechanics, oganesson has standard shell structure, like all other rare gases like radon and xenon. Okay, nothing special. But if you replace non-relativistic equations with relativistic equation, you see this is totally smeared. Shell structure as we know it, according to Mr. Bohr, is gone. So at this point, the fundamental model of atomic nuclei breaks down. Valence electrons are distributed more or less uniformly, and this guy is going to be reactive. And this is actually shown here. The oganesson is predicted by quantum chemists to be the first rare gas with positive electron affinity, which means that you can attach an electron to neutral oganesson atom to produce an anion. Okay, and this is shown in this diagram. Okay, those are rare gases, as you can see. They all have krypton. This is argon, krypton, xenon, radon. They have zero affinity. You cannot attach an electron to atom, but you can attach it to oganesson. So oganesson, because of this absence of shell structure in the valence shells, will be reactive. Oganesson is a very special gas. As a matter of fact, it is not expected to be a gas at room temperature. This shows the systematics of measured and calculated this is the melting boiling temperature of oganesson. As you can see here, that the melting temperature for oganesson is 150 Celsius. 150 Celsius. At this point, oganesson will melt from solid to liquid, which means that at room temperature, it is a metal. It is expected to be. So, as you can see, it is a very special rare gas element. Some chemistry has been carried out on superheavy elements. So this shows basically the situation. So one atom at a time chemistry was done for fluoronium, nihonium, copernicium. As you can imagine, those are extremely difficult experiments because the production rates of those superheavies are so low, okay? So far, from the point of view of some basic chemical properties, no dramatic changes have been found as one goes to fluorovium. Fluorovium is here, okay? Fluorovium behaves pretty much like its homologs, mercury, cadmium, and zinc, for instance. So they are all expected to be like rare metals, transition metals. Okay, but of course there are other properties which suggest that those elements are different, and oganesson is supposed to be extremely different. There's one interesting thought which I would like to mention. So, according to International Union on Pure and Applied Chemistry, I will just quote it because it's important. The discovery of a chemical element is the experimental demonstration beyond reasonable doubt of the existence of a nuclei with an atomic number Z, not identified before, existing at least 10 to the minus 14 seconds. Why 10 to the minus 14 seconds? You will say, this is such a... It's not that difficult to get 10 to the minus 14. This is decimal point 14 seconds, right? Very short time. But we have to remember that the nuclear time scale is 10 to the minus 20 seconds. So 10 to the minus 20 seconds is typical time for the nucleus, you know. And so the nuclei can exist even at so short times, okay? So this 10 to the minus 14 seconds is the time which is required to form atomic cloud, electron cloud around the nucleus. So imagine what happens if the nucleus in the center of the atom exists, but it has lifetime 10 to the minus 17 seconds. Okay? The nucleus is in there, you know, but electrons cannot form because they need 10 to the minus 14 seconds. So one can easily imagine a situation that the periodic table will end because atomic nuclei will be too short-lived. Okay? So this will be a very interesting extension of the Mendeleev table, not for chemists, of course. We will talk about nuclei without electrons, which live a short time, and the chemistry will end. Okay, so let me summarize this. Okay, so what we have learned so far. So elements up to element 118 have been produced, and the end of the nuclear chart has been extended all the way to oganesson, 294. The stability of superheavy nuclei is governed by alpha decay and spontaneous fission. Their half-lives increase with neutron number, and this is consistent with this expectation that there is this island, or the region of enhanced shell stability around neutron number 184. And we are in the process of searching for new chemistry due to extremely strong relativistic effects. But this is really the beginning of this new adventure. You know? So people are searching for elements beyond Z118. As we talk, there are two experiments going on in RICAN and in Dubna, searching for elements 119 and 120. So wait, and this might happen soon. So there will be an expansion of the periodic table, and poor people in Murcia will have to change the facade of the chemistry building. Nuclei beyond 294 oganesson, of course, are going to be found, new isotopes. So we will try to make strides to go to this region of enhanced super heavy, longer-lived super heavy elements. We would like to understand better those exotic topologies of densities with those hollow interiors. And of course, this whole area about super heavy elements in the cosmos. Can they be produced in stellar explosions? Okay. Can you get some signals about super heavies in the cosmos by looking at elemental abundances? This was partly discussed during the first lecture by Artemis Spirou. So this is the new laboratory in Dubna in Russia called Super Heavy Factory. which is going to be built soon, and they'll be running super heavy element research 24/7 there. So there will be lots of discoveries coming from Dubna. Applications. Well, if you are a fan of science fiction literature, you will find many applications. You know, element 112, according to the authors, is a popular fuel in spaceships by aliens. Okay. Well, element 113 is a rock band from Minneapolis. Jack Daniels, after tennessine was discovered, produced a special single barrel brand of Tennessee whiskey, element 117 Tennessee. So people try to commercialize, as you can see. And when I went to Livermorium celebration in Livermore, you know, we were offered this souvenir. Okay. So yes. So we're a long way off from the end of the nuclear chart and the periodic table. We really do not know how we end because of this interplay between physics and chemistry of very heavy nuclei and atoms. So this is going to be a fantastic adventure. So FRIB, as I said, will have its role in this, and there is, as you know, this science festival at MSU, and next week on April 6th, between 1:30 and 2 in this very room, I'm going to discuss some elements of science of FRIB. So if you are interested in this, please come. And in order to finish it properly, there has been a new version of the periodic table song. Okay? And it's 9:25, so we can still do it. Updated for the new element.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air with oxygen so you can breathe in, fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, then argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gases stable, halogens and alkaline. Neon, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead that is meant for your tummy, polonium, astatine would not be yummy, radon, and cesium will last a little time, radium, then actinize at 89. This is the periodic table, noble gases stable, halogens and alkali react aggressively. Each period will see new outer shells will electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, bromium, nobelium, nobelium, lawrencium, rutherfordium, wm, spherium, borium, hesium, meitnerium, dubsidium, mercenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and oganesson, and then we're done.
Okay, so as
Thank
you can see, this has been properly updated. Okay, this one. Well, thank you very much.
Thank you, Witek, for a lovely talk. I'm sure there must be questions, so volunteers, people would like to ask a question. Yes.
I'm interested in those density plots that suggest that kind of like a donut configuration. Is that expected to be physical? Like, might actually exist, or is it a breakdown?
Oh yes, very physical. I mean, those are the calculations which are done through, using standard density functional theory methods, using realistic interactions. So actually, similar distributions with the central depression are expected in nobelium. In nobelium 252, 253, and the radii of those nobeliums have been measured last year at GSI in Germany. And those radii are totally consistent with those densities, with those small depressions. So I'm very optimistic that those are realistic. When one goes to element 150, of course the hole will be big, but also other topologies are expected, like a toroidal shape. This is also going to be allowed by those strong electrostatic repulsions. So, pretty fantastic perspective.
Next question. Yes.
Can you further explain how relativistic effects affect the electron shells?
Yeah, so one of the most important, first of all, as you know, as the velocity increases, the mass increases. So there is, of course, the velocity effect on the mass. So as the mass increases, the radius of the lowest orbit goes down, the radius of the Bohr orbit is reduced because the mass is in the denominator, right? So those, the closest electrons, the electrons closest to the nucleus, S and P electrons, are being attracted to the nucleus, are getting close, okay? And they are shielding the other electrons, you know, with high angular momentum. And this is a very important stabilization effect. But there is a spin-orbit interaction, which is a very relativistic effect. And in normal atoms, spin-orbit splitting is small. But in oganesson, the spin-orbit splitting for 7p shell is 10 electronvolts. And this gives rise to this uniform behavior of the valence electrons. Sorry, technical answer.
Other questions?
Yes.
So I don't have a really good understanding of a lot of quantum mechanical stuff.
But of course.
It can be sort of obscure. But I thought that we visualize the electrons as sort of standing waves and not actually having a translational velocity.
Yes.
So I guess I don't understand.
So the picture which I showed with those shells is very schematic. But also this picture in the beginning when I showed electrons as a cloud.
Right.
So the picture of a cloud is certainly more proper from the quantum mechanical point of view. So you should understand those little rings, say, as the regions where there's the highest probability to find the electron. In reality, there is always a finite probability to find the electron in any point in space.
But to have a relativistic mass, doesn't it have to have? Isn't there a translational velocity associated with that somehow? And I guess I'm not seeing how.
No, of course. They are moving. Those electrons move, of course, with certain velocity around, well, in a simple picture of the Bohr, okay, let me put it in this way. When you solve the wave equation, relativistic wave equation for the electron, of course you get the wave function. If you will think about Bohr picture, okay, which is perhaps more popularly known, you can introduce angular velocity for an electron, okay? Angular velocity will be then related to linear velocity through the relation v is equal to omega times r. R is the radius, and you have something which is close to velocity of light. Yes?
I'm curious about this donut-shaped possibility. Is that due to relativistic, quantum effects?
This is just electrostatic repulsion.
Whereas an occupancy could actually exist outside of the energy well. Is that what we're talking about?
No, energy well is totally is related to the density. Energy, potential well and densities are self-consistent in this point of view. It's totally classical effect because Coulomb interaction is inversely proportional to the distance between two charges, 1 over R1 minus R2, right? So the larger distance between charges, the less the Coulomb distraction. So it is easier, if you have very strong Coulomb interaction, it is advantageous to move protons to the surface because this reduces the overall Coulomb distraction.
Yeah.
Yes?
Can polymeric kind of chain-like nuclei exist?
So one predicts not chain-like by band-like superheavy elements, but chain-like nuclei, yes, they are expected to exist in light systems. You know, those are alpha particle chains, like several alpha particles forming a chain. And there are such states in the light nuclei, like in neon 20, neon 20, you can think of neon 20 as made of 5 alpha particles. So there is a state which one believes corresponds to 5 alpha particles along, forming a chain, linear chain. So there are such, but this has little to do with superheavy.
Other questions?
If you have not graphed some nice handouts, there's a popular article on superheavy elements, nuclei. Please help yourself if you have not collected it yet. Okay?
All right, let's thank Witek.